Good morning. And today we have exciting topic. We discussing, well, the second presentation also on about Magnetorheological Cementitious Nanocomposites. And I think we were working for quite some time on the similar topic. And when I saw presentation of Grit back in 2020, I said, oh, I have also a slide. I need to include one slide in my presentation because I was not thinking to talk about it. But it's really exciting topic because when I was thinking what we can do in terms of 3D printing, in terms of rheological control, and again in nanotechnology, what nanotechnology can do this to improve the rheological response, give us freedom to control rheology. And two students worked with me. A partner, I think she is here, must be in the room, and Rosie, she worked with us as well. So PhD student and undergraduate student work on this project with me. And well, I'll briefly speak about challenges with concrete. I removed a lot of content about nanotechnology, nanomaterials, but I'll fill in as possible. And when I was looking at the presentation, I wanted to look what happened like 100 years ago. What was concrete like back in 20s? And I came across, I did search through Portland Cement Library, and I came across this figure. I don't know if you recognize the face, but it is actually Edison who came in the search. So, well, he was the first guy who constructed concrete pavement in New Jersey. Wow, it was some sort of discovery for me, and I just look further, and he worked on formed concrete, and I was also not aware of it. To my shameful, but you know, I was chairing cellular concrete committee, and I was not aware that he was actually the first guy who invented it. And also he developed free-flowing concrete, self-consolidating, like almost self-consolidating concrete of the past. And he built a number of hurricane-proof concrete houses, which are apparently still there. Maybe they lost their initial beauty, but they're still there. So basically, he proclaimed that age of concrete back 100 years ago. And I think if we look at what happens now, and this is like construction from Milwaukee, well, it looks flowable concrete, same as Edison used in the past. And of course, with some modern modification. But what is really next? Where are we going? What we can do? How we can do job better? Obviously, 3D printing is interesting approach, and there are great potential. Yesterday we had a forum, 1 to 3 forum, discussed all the challenges related to 3D printing and design of the structures and new approaches. And obviously, while we are still debating how to do it, practitioners are there exploring the field and building beautiful structures out of 3D printing. Obviously, researchers very often they are focusing on fundamental studies and looking at the paste level. And between the paste and the scale, obviously there is a big difference. And it is what I realized that it is more challenging to do 3D printing at the paste level, and it's really more forgiving technology at mortar level when you scale it up. So this is good news for us. But what are the challenges with 3D printing? Obviously, we need, from one side, we need extremely fluid material because the transport is happening and deposition is happening when material is still fluid, and you need really perfect flow properties. But as soon as it is deposited to the intended location, material should freeze. And basically, well, our material cannot behave like switch on and switch off, or doesn't respond to magic words. But can we design material so it responds to some other action? And specifically, magnetic field was one of the interesting approach. So magnetic field, this is something which we can induce, and especially with very powerful permanent magnets, You can even do it without much of the energy consumption. So obviously there are challenges, and especially if we want to have high performance concrete printing, etc. So one of the ideas I had was, we produce ultra high performance concrete with nanomaterials. Can we 3D print this material? Obviously it was extremely challenging. Obviously we need to look at material optimization, basically fineness of aggregates, and do optimization starting with aggregate proportioning to particle size proportioning. Obviously using advantages of some components which we commonly use in concrete, like beautiful particles of fly ash, can facilitate the flow, and which we extensively use in ready-mix industry. And at the same time, we need to control the rheology, and nanosilica, for example, is a perfect material to control the rheological response. Basically, was good question about viscosity modifiers, but as we already demonstrated, nanomaterials such as nanosilica or clay, nanoclay, and or other nanomaterials are perfect viscosity modifiers, which are not interfering with hydration processes, actually even accelerating hydration, and they are really way better components for self-consolidating concrete. So this is the setup which I saw at Ghent University, and I was already playing with this extruding gun, and I was trying to achieve vertical printing, and it was like the challenge for us. But when I saw the setup in Ghent, I came home immediately, like in 2 weeks. We put together another setup, so instead of printing vertically, we put it horizontally. And basically, again, it comes to the point how to test quickly mix, and one of the challenges is actually with 3D printing. You produce the mix and you don't have testing standard, you don't have way to test it effectively, and you feel that you need this extensive 3D printing equipment, you need robots, etc. So the expense, even like at research lab level, is considerable. But with such a setup, again, Milwaukee too, I'm from Milwaukee, so I get it for free, the gun. And so you can use to test extrudability, but also a moving platform, and again with changing support. So you can see this white plastic support. You can keep extruding, you can keep depositing. So basically you are in sample production mode, and you don't again need to have a huge system. So how it works? So, and my Mac was not operating, not showing this video yesterday, but I hope this ACI, yes, computers, they use PC, so it works well. And so basically you deposit, you can test your mix, and again, researchers, we like to work with smaller samples and to evaluate them, etc. So basically you keep depositing, and I was thinking to accelerate the movie. But basically, let me see if, I think it's, okay, I think it's now confused. No, it doesn't want to do fast forward, unfortunately. And anyway, so basically we deposit layer by layer. We can build as many layers as we want, and we can observe the response immediately. And basically, as a result, we can see different compositions. We can compare them. We can compare thicknesses of the layers. We can check the geometry. And buildability can be easily evaluated. I think this approach can be easily converted to the testing, and we can easily generate a document which can help us to test a good mix and achieve the material properties optimization using this system. And again, for example, one of approach how to design the mix, we simply can use classical flow table, and we can easily distinguish the printable mix from a non-printable mix. And with 3D printing, you don't have that much freedom anymore. You have very narrow band of the compositions which can be extrudable and which can be deposited. And this is classical mixes. You don't have any chemical admixtures. You don't have here viscosity modifiers, just simply regular mortar. And basically, well, mortars are a little bit richer than classical ASTM test we do for compressive test or for classical flow table test. So again, those are the approaches we can use to test the material. And finally, we come to the point, so we still need to characterize material, and we need to use rheological models. And what we have as a classical model, like Newtonian response or Bingham response, and obviously with 3D printing, we like to see yield in the system. So if Newtonian system cannot be used for 3D printing, because you need material to sustain the stress. And so the reality, the Bingham model is represented for many systems by Papaanastasiou model. So you have a curvature associated with the curve. And some systems, like we tested systems with 50% of fly ash and different nanoparticles. You can see that bottom line is just a reference system with 50% of fly ash, and it is perfect Newtonian response. As soon as you start adding nanoparticles, and I usually use very small quantities of nanoparticles, 0.25, normally 0.25% of cementitious materials, you can change it to Bingham or Papaanastasiou response. And again, you have loading and unloading curves at certain time period. And so the challenge again, when we use fly ash in the system, it's a challenge to produce right response. But what is ideal response? Bingham is good, but what happens if we can have a material which can have additional stiffening at lower shearing rate? Because when you deposit, your shearing rates are reduced to zero. So if we can build have a material with such a rheological response. And I look at the tests with nanoparticles which we run, and I realize some of experiments resulted in this stiffening mechanism, what we call sticky particles model. And this is the response actually which is extremely beneficial for 3D printing applications. So this is response of nanosilica when system would show relatively small yield, but it actually has very high stiffening and very low shearing rates. And well, we have nanosilica on the top, nanoalumina is in between, and this is just response of pure Portland cement system. So very small quantities of nanoparticles can change yield, but also can provide additional stiffening. This is what we observed. And again, nanosilica and nanoalumina here compared. Well, results were published at ACI Materials Journal some time ago, and you can look at it more, but the experiment we run also, in addition to nanoparticles, we like to add and the fly ash, and also we tried magnetite particles. So in addition to nanoparticles, which were used in very small dosages, magnetite is not exotic really material to us. It is black pigment which we used for architectural concrete. And usually 5% is normal dosage if you want to change the color of concrete to desired shade. And so magnetite, again, it's more expensive than Portland cement, but it is something which is in our toolbox, which we use in concrete technology. And again, it is highly magnetic material, and it is attractive component. Well, why I am talking about fly ash? Because fly ash is magnetic by itself as well. and especially type F fly ash, which has considerable quantities of iron oxide. And here idea is to, again, incorporate magnetic components and including nanomaterials, which can be helping with viscosity control, and material to respond to external magnetic field. And again, switch from solid, so liquid to solid is desired response, which we target here. And again, this is our setup, classical rheometer, which used for different experiments. And we tried different geometry, parallel plates, stirred plates, and it didn't really work for the range of the viscosities and the range of the shearing stresses which we tested. So we had to switch to Van geometry. And in addition to control the magnetic field, we had to build the electrical magnet, and we use constant field, but can be easily switched to AC as well. And and you can see one of the first experiments which we ran quite time ago. So it was like one of our first experiments to take to test the. I don't know if it runs. So basically, you see you have a funnel with I believe 8 or 10 millimeter opening there, and you have the power supply on the right, and student is switching the now electrical field is in, and now it's off, and so material starts to flow. Pay attention that you have first chunks of material which was magnetized, and in the capillary, and as soon as it runs, you have free flow. The funnel is full, so you have enough material, enough pressure for material to flow. But obviously, these chunks are magnetized material. Now we have free flow of the material through the funnel. And again, this was one of the first experiments to demonstrate the concept and basically use this setup as a magnetic valve. Well, when we apply magnetic field, rheological behavior is changing. And for example, behavior, and this is pure Portland cement system, and I already reported on the system with the system with Portland cement, and this is system with magnetic field. So magnetic field is really helping us to enhance the response and provide additional stiffening. And specifically, both yield and stiffening stress are enhanced. If you look on the right-hand side, we have a system with magnetite powders. And again, magnetite was working well to enhance the response of a reference Portland cement system, for example, but maybe not as great as in enhancing silica fume system. And a reason for that nanoparticles we used, actually they were not magnetic. So when you have magnetic inclusion, basically magnetite and I don't have fly ash here, magnetite particles, and they were surrounded by non-magnetic particles. They were preventing actually contact and building the chain. So basically, this is where non-magnetic particles may not interact well with magnetic particles. And so this is the reasoning when we like to see magnetic nanoparticles to be used in the system. Well, when we use system with fly ash, and I initially demonstrated that this system is not very suitable for 3D printing application, but you can see that Newtonian response from reference fly ash, 50% fly ash system, can be converted to Bingham response, and systems with nanoparticles response was really enhanced. Extremely fluid systems can be really stiffened significantly by applying magnetic field, especially systems with magnetite powder. And you can see that complete transformation of reference material with just its 45% of fly ash and 5% of magnetite powder. It was Newtonian behavior without magnetic field, and with magnetic field, considerable stiffening is achieved. Again, compatibility between magnetic inclusions and nanomaterials needs to be further investigated. To summarize the effects, I can compare yield stress of material without field and when we apply magnetic field, and you can see that enhancement of the yield was demonstrated for all the materials we tested. And another important figure, that in some cases we had also stiffening stress was also enhanced for some compositions. And specifically, the magnetite addition was very beneficial to achieve this top level of the levels of performance of the investigated systems. Again, magnetite is not nanoparticle, but it is smaller than 1 micron, so sub-micron particles. And they were also providing a very unique response. I think I have maybe 5 more minutes. Okay, so now question was about how to make it cheaper and where we get this wonderful magnetic particles. Well, fly ash is a perfect source for us. We see less and less fly ash available for our projects. There is still fly ash deposited, and this is the setup we had for beneficiation of fly ash. And basically the idea is, can we extract magnetic fly ash from already relatively rich types of fly ash? And again, we had few products which were ranging from 11% to almost 19% iron oxide. And those were perfect candidates to study. So we run milling and we run magnetic separation. So basically, milling, we use the vibrating mill. Normally, we use wet milling. And we would use magnetic separator to separate slurry of non-magnetic ash, which would, of course, contain some magnetite particles, magnetic particles, and the perfectly magnetic ash, which would also contain reactive aluminosilicates, etc. So it's not really pure separation. But again, having two products was extremely interesting idea for us. And so we ran additional experiment with fly ash, just 10% replacement, magnetic ash, non-magnetic ash, with superplasticizer mainly, but also we run non-superplasticized mixtures. And what we realized that by adding magnetic ash, you can see that non-magnetic ash was actually providing us a better yield and the stiffening as well, because of ultrafine particles. But magnetic ash was not as reactive without magnetic field. As soon as magnetic field was applied, the response was very similar. But the response, non-magnetic particles were not affected by magnetic response. And we plotted again similar distribution for yield stress and enhancement of yield stress by magnetic field, and the same enhancement of the build-up stiffening stress due to magnetic field, and this is just in percentage. So you can see both in percentage and absolute values that magnetic ash was really showing excellent enhancement of performance. Basically 350% maybe for build-up stiffening stress, and also about 350%, 450 something percent for enhancement of yield. So those are the results. And again, what we see that if you just simply use sometimes fly ash systems, it's difficult to achieve the desired performance. Obviously, we can improve it with nanoparticles, but and nanoparticles can provide you desired response with sticky particle, which we described by sticky particles model. And this can be a good solution. But if we want to design the magnetorheological response, and again, our field was also 0.1 Tesla for this experiment. This can really change the rheological response, but we need to be very careful in balancing the type of nanoparticles we are using, type of magnetic particles we use in the system, if we want to be effective. Obviously, I really like to explore more sticky particles model, because this is something I believe is extremely useful for 3D printing. Obviously, fly ash beneficiation, I think it is really interesting direction which can be further explored, and to harvest very cheap magnetic particles which are available to us. Brief update, we are going to discuss more questions about nanoparticles in effect in cementitious system in Catania, in Italy, July 18, and July 12 we have another July 11, sorry, workshop of RILEM. And ACI Committee on Nanotechnology is searching for good students who want to present their results and need financial support. So we give 5 scholarships for $1,000 each, sponsored by Concrete Nanotechnology Society. And so if you are a student, please apply, basically email to me, to Maria Consta, and submit abstract. Obviously, we will be happy to support the trip. Well, those are my sponsors. Really thankful to many sponsors, students who worked on the project. And again, if you have any questions, email us here. You can contact me. We'll be happy to give you maybe more information if needed.
Thank you, Konstantin. Thank you for this interesting presentation. I think we have time for questions. So, any questions? If you have any questions, please go take the microphone.
Hey, Konstantin, did you use a powdered nanosilica or liquid dispersion?
Liquid dispersion, liquid. Everything is liquid form, both nanoparticles. Well, good question, because we had nanoalumina, we had to disperse by ourselves.
Okay.
But
So you suspended that?
Yes.
And then dispersed it? Okay,
Yeah.
very cool.
I mean, if we have more time, I do have slides which I can show about dispersion, but it's kind of different topic.
I'll email you.
Yeah, sure.
Any other questions?
Konstantin, I didn't understand why with ball mill grinding you increase the magnetic component. What is the mechanism?
Well, first of all, if we look for magnetic inclusions in fly ash, well, I have this beautiful, well, this is the picture, right? So basically, sinosphere would contain magnetic portions, non-magnetic portions. I don't think the magnetic material is sitting like as a separate grain. So without, so it's embedded into the structure, alumosilicate matrix. Consider muffin, you know, and you have this perfect grains embedded, or berries embedded into the structure. How to extract them? So you need to break the structure out and to have smaller chunks. And what we demonstrated, so you see with milling, you have, this is a distribution for magnetic and non-magnetic. And you see you have 19% of material which is iron oxide. And after 3-hour milling, you have 22% of magnetic material harvested. Doesn't mean that this is 100% iron oxide based, because you still have alumosilicates there. And what we demonstrated, I removed the slides on hydration. We demonstrated that magnetic particles, they are working very similar way as reference fly ash on hydration. So we don't see that pozzolanic activity is completely destroyed. So basically the idea is we still like to have magnetic particle, which is magnetic on one side, on another side is still preserving reactivity. And here by initially well, even after 1 hour milling, sorry, we had 60% of magnetic particles. So magnetic particles were embedded into the matrix. Upon milling, the quantities are reduced, but the concentration of magnetic particles in this magnetic portion is increased. So this is the reason why we need to mill and have, obviously particle size reduction is also very useful for pozzolanic reaction and the reactivity of the particles. So those were really good products at the end, but both products were very beneficial.
All right, we are going to take the last question so that want to make sure that we remain on time.
Well, thank you for giving me this minute. Well, I want to come back first on Edison. It's marvelous that you showed the houses of Edison. And at that time, they built a few ones, but then it stopped because of huge problems. They could not pump, they didn't have pump, so it was an Archimedes screw to bring the concrete to the top. And then the filling was a huge problem. Of course, they didn't have superplasticizer as we have now, so it was only with water. But if you add water,
so it was almost like 3D printing mix.
Well, yeah, but that's not flowable enough, and then adding water makes it more like segregating, etc. So it failed. But he was visionary. That's true. Yeah. Actually, he also made concrete furniture like pianos, etc. But that's another story. Now I have a small question. It's not on the scientific content, but on, let's say, boundary conditions of doing research in a lab, because that's also important. You show the setup of the electromagnet with copper wires, etc. We also do this in our lab, but then the safety department is also always getting like crazy. What are you doing? What are you doing? So I was wondering, how is the situation here in US? Is safety strictly controlled by some external group in your university? I was just curious.
I think in terms of like they're more concerned with powders and the storage of chemicals. I think if it is and yes, it is a lot of questions asked about like ventilation and other things. But I think on the terms of electrical, everyone is relaxed. We have a lot of electrical, we have big electrical departments. So I think we are doing like smaller exploration than than others. So we are like smaller threat to the to the safety of. I mean, it's. All small currents, and we don't use like Tesla high power and high charge things. So I think it's all within the limits. All safe.
Thank you again, Konstantin.